Hi, it's me again with a very short video this time. I want to basically wrap up on my classical explanation of the anomalous magnetic moment of the electron, which I show here. I wrote a paper about that. They're basically two modern explanations, quantum electrodynamics, and then sort of very speculative model. My model was simple, but I wanted to ground it also because I left some options open, and I'm gonna immediately show these options that are open. One of them basically was, in this model of ours, where we assume that an electron has a structure which consists of a sort of a hardcore charge, a tetrabeweging charge, whose radius or whatever a dimensional characteristic you want to give to it is of the order of defined structure constant alpha, gives effectively like the experimental results that we have, the anomaly and the magnetic moment and then Thomson scattering. For the establishment of really the theory, I will refer to my previous video. I won't repeat myself. But a crucial element in there was that, yeah, that Thomson scattering, that very hard scattering, elastic, inelastic. The photon doesn't lose any energy when it scatters back from an interaction with an electron. How do you model that? And I wasn't very clear on that. The Thomson scattering cross-section radius has a factor in it, which is different from the squared radius of the classical electron radius. Which I single out here. The scattering angle has a pretty traditional formula which makes it oscillate as the the probability as the probability function. It will scatter more in one than the other direction, and the basic function underlying the probabilities is 1 plus cosine square times that scattering angle. That's the differential cross-section formula. It gives rise to a whole series of questions. When you look at this function here, this one here. Well, it looks like this, and it brings a lot of questions. What's the average value of this thing between 0.5 and 1, and what does it make? The thing I want to refer to is a chat that I will make public right now. You can copy it, chatgpt.com, see, and then this whole series. It's like, okay, what does it really mean here? Because if we fire photons into an electron, then we get this derivation of the cross section, and there's so many intricacies to it that it's not easy to make sense of it. So I would recommend you go through this public chat, which I'm a bit ashamed of because I'm asking very stupid questions to ChatGPT. But the answers it gives are very good. And yeah, I ran out of time with ChatGPT-o1. Tomorrow morning I have the right to get more answers. In the meanwhile, you can download latest iOS or Android APEP to get more natural real-time conversations with advanced voice, with senses that respond to humor, sarcasm, interruptions, and more. I'm not so interested in that, so I will acknowledge that I've hit my plan limit for $20 a box. But go back to our presentation here. The probability distribution that is charted out here is very interesting. I think it should expand over, it should go from 0 to 2 pi, somewhere here. But there, ChatGPT gave a rather convoluted answer. Which is, yes, you're right. In any case, the differential solid angle element involves not only the polar, but also the azimuthal angle, and etc., etc. And so we have a Thomson scattering cross-section formula that involves, a domain of the function which goes between 0 and pi, and not between 0 and 2 pi. I said it's quite public. Notice the site address, just chatgpt.com 67, etc., etc., and copy that to your browser and continue the conversation. I'm amazed at the geometric. I mean, this conversation started off very well and not so well, in the sense that I had asked a question and I had to correct it for a 1/2 factor based on very simple geometric considerations, which ChatGPT-4o may or may not consider. That's not a big problem. The real thing is indeed about let me pull up the this probability distribution of scattering of a photon is a probability distribution which goes between, as you can see here, from 0 to a bit less than 0.5. The integral between 0 and pi is 1, so that's a proper probability distribution. It has two maxima, one at 9.095 and the other one at 2.1. I think we should double that. There's 1/2 factor in it that I'm working on now with ChatGPT to sort of resolve that, because the cycle of the probability distribution should be between 0 and 2 pi, not between 0 and pi. It will probably be solved looking at the rather elegant symmetry of the blue function here that you see right in front of you now. So I will get back to you on that. And that's basically it. The next thing I'm going to talk about is much more serious, is about symmetries in space. Charge symmetry is easy. Electrons, positrons. I said it. We will introduce color charges maybe, or some kind of color typing again, because a positron is not the same as a proton, and so an electron will annihilate a positron, but not a proton. Will be in some dance and this and that. We talked about that in previous lectures. The P in CPT symmetry is a mirror symmetry, and I said the most fundamental asymmetry in nature is the electromagnetic force as we know it. The magnetic field vector follows the electric field vector with a phase difference of well, a direction. Their directions are different. 90 degrees. We could imagine sort of an anti-force whose characteristics would be that the magnetic force would be yeah, also 90 degrees different from the electric field vector, but on the other side. It's an intriguing hypothesis. I do want to pull up my blog here. It may explain this here. New day Keon decay modes. They weren't possible. The hypothesis has been based on the fact that certain decay reactions weren't possible. Now they seem to be possible. I mean, that's what we are talking about here. I'm not going to go into too much detail there. Let me go back to my presentation. Time symmetry, that's quantum theory 101. I don't know if I pulled it up, my very basic, yeah, lecture 1 on physics modeled according to Feynman is this. If you would assume time travel to be possible, then you get you know, the whole mathematical and physical apparatus falls apart. A particle can be at two positions at the same time, or you know, at the same time it can be at two different places. It doesn't make sense. Time travels in one direction only. That's the definition of motion. That's the definition of a well-behaved trajectory in space-time, and that's it. We've been talking for 12 minutes now, so I do gonna stop to see if I have anything to add. This is here a graph of Vassallo and Dr. Kovacs. I'm in touch with them now. They will solve problems I can't solve. This is sort of how complicated the trajectory of a charge really is in an external electromagnetic field. I would refer you to my recent paper. Let me pull that one up. Yeah, that's this one here. The anomalous magnetic moment of the electron, an easy geometrical explanation. Of course, it's not easy. But I described that there, the complexities of, you know, imagining or modeling various correction factors to the theoretical magnetic moment of an electron. I think we'll get there. I'm 16% off. There's a lot of ambiguity on sort of, you know, what's the model that experimental physicists use to measure the magnetic moment of an electron. You know, based on that, you get corrections between 5 or 50% to the values they churn out. So I'm gonna leave it at that. I'm at 15 minutes, and that's okay. I will see you next time. I wish you a very nice